Lecture 6, Part 2, Discrete Probability Distribution. In this section, we'll be looking at two types of probability distributions. One is going to be called the binomial, and the second will be called the Poisson distribution. Let's start with the binomial distribution. So in a binomial distribution, there are only two possible outcomes on a particular trial of an experiment. The two possible outcomes are success, failure of the experiment. The outcomes are mutually exclusive, and the random variable is a result of counts. So either you have 0 successes, 1 success, 2 success, 3 success, etc. Each trial is going to be independent of any other trial. Now, one other key characteristics of the binomial is that it will have an upper limit of the number of possible trials in every single experiment. So the equation for the binomial probability distribution is written this way. It's written as n combination x. The n is the number of times or trials that there is in total for the experiment. X is, we're defining it as the number of successes we're looking to find the probability of. Then we multiply pi to the x. Pi is the probability of success on each trial, and that will be consistent across the problems that we work with. And then the last part is 1 minus pi, which is the probability of failure. If pi is the probability of success, 1 minus pi is the probability of failure. And this is raised to the n minus x, which is, again, the number of trials, minus the number of successes. Let's work through this through an example. So, example, there are 5 flights daily from San Francisco via Southwest Airlines into LAX. Suppose the probability of any flight arriving late is 0.2 or 20%. We can put a 0 there just to help clarify that a bit. Now, in this case, we have an upper limit in terms of the total number of trials, and the number of trials in this case is going to be 5 per day. The probability that any one of them is late is 0.2. So in this case, we're going to be assuming that our favorable outcome in an experiment in this case is going to be what is the probability of a flight arriving late. So if the probability that a flight arrives late is 0.2, then the probability that a flight arrives on time is 0.8. The three values we're going to be calculating is going to be what is the probability that none of the flights are late, what is the probability that 3 of the flights are late, and finally, what is the probability that all the flights are late? The next video will go into detail on how to calculate each of these components. So, example 1. There's 5 flights daily from San Francisco via Southwest Airlines into LAX. Suppose the probability that any flight arrives late is 0.2. In this case, we're going to use arriving late as our favorable outcome. So first, why are we using the binomial distribution in this case? Well, first off, we have an upper limit. So in this case, 5 flights is the total maximum number of flights in any given day, and therefore we're using a binomial distribution. So first, let's list a few things. We know that the total number of events or experiments is 5, so n is 5. And the probability that any one flight arrives late is equal to 0.2, so pi is going to be 0.2. We're going to find a few probabilities together. So first, we're going to find the probability that none of the flights are late. Then we're going to find the probability that 3 flights are late. And finally, we're going to find the probability that all of the flights are late. So let's start with the probability that none of the flights are late. Let's plug in the information into the equation. So we have 5 combination 0, 0.2 to the 0, and 1 minus 0.2 to the 5 minus 0. So let's find each individual component. So first, 5 combination 0 is equal to 5 factorial over 5 minus 0 factorial times 0 factorial. Please don't forget that 0 factorial is in fact equal to 1. So 5 combination 0 is going to be equal to 1. anything combination 0 is equal to 1. Now, point 2 to the 0 is also equal to 1. And finally, the only thing we really have to calculate in this example is that 1 minus 0.2 to the 5 minus 0 is equal to 0.8 to the 5th, which equals 0.3277. So the probability that none of the flights are late is 0.3277 or 32.77%. Now let's look to find the probability that 3 flights are late. So to get the probability that 3 flights are late, let's plug it into the equation again. So we have 5 combination 3, 0.2 to the 3rd, 1 minus 0.2 to the 5 minus 3. So first, 5 combination 3 is equal to 10. 0.2 to the 3rd is equal to 0.008. And finally, 1 minus 0.2 to the 5 minus 3 is 0.8 squared, which equals 0.64. Now, to calculate the probability that x is equal to 3, we're basically going to find the product of those. So we'll have 10 times 0.008 times 0.64, and this will be equal to 0.0512, or the probability that 3 flights are late will be equal to 5.12%. Finally, let's go to the third value, which is the probability that all the flights are late, and therefore x is equal to 5. So once again, we start with our equation, 5 combination 5, 0.2 to the 5th, 1 minus 0.2 to the 5 minus 5. So 5 combination 5 is going to be equal to 1. So anything combination itself is always equal to 1. 0.2 to the 5th is equal to 0.00032. And finally, 1 minus 0.2 to the 5 minus 5 is equal to 1. So what is the product here? 1 times 0.00032 times 1. We find the probability that all the flights are late is 0.00032, or 0.032%. The mean and the variance of the binomial distribution. These are actually quite simple compared to how we calculate the variance of the discrete probability distribution. In the case of the binomial, which is a special case of the discrete probability distribution, the mean is equal to n, which is the number of trials, times pi, which is the success rate of any given trial. In the variance of the binomial is just n, the number of trials, times pi, the probability of success of any given trial, times the probability of failure, or 1 minus pi, of the experiments. And that'll give us the mean and the variance. So in the case of the airline flights, we knew we had a total of 5 flights per day. The probability of a flight being late was 0.2. So based on that, we would expect, on average, 1 flight to be late per day, based on the probability and the number of trials. The variance would simply be 5 times 0.2 times 0.8, so the variance would be 0.8. If we wanted the standard deviation, we would just have to take the square root of that variance, and we would get the standard deviation would be 0.894. So this is just to check your answer and to kind of test out the different values. We could actually calculate the probability of 0 flights, 1 flight, 2, all the way up to 5. We were able to calculate 0, 3, and 5 flights being late. But if we calculate every single one of these, we can actually replicate our discrete probability distribution that we saw earlier by taking each flight, multiplying that by the probability of the flight being late, generating this distribution. And recall that to find the mean of a discrete probability distribution, we just add up x times p of x, and in this case we get 1, which is exactly what we got using the shortcut equation. From then we do x minus the mean squared, and then x minus the mean squared times the probability of any given x. And when you add up that column, you notice we get a variance that is just slightly different than what we calculated before, but it's super close. And if we really round to 2 decimal places, we would get 0.8. Now, this method is of course more precise. However, it's so close that it doesn't really make a huge difference, and it saves so much more time using the shortcut in finding the mean and variance. This is looking at the probability distribution graphically. Notice that here the probability of 0 flights being late is 0.32, 1 flight is 0.4096, etc. Now, if we were to discuss this distribution, we would say that it has a positive skew. And just by looking at it, we'd even notice that the most likely outcome is that 1 flight is late, and therefore this makes sense that the mean of the distribution, or the average value of the distribution, is also equal to 1. How does the shape of the distribution change when we change pi? Notice in this case we have a pi, a probability of success that is very low, or 5%. Here we're keeping n constant just to remove that effect. Notice here we have a severely positively skewed distribution where your most likely outcome is that you have 0 successes. But as the probability of success rises, what we see is that the shape of the distribution is going from a severe positive skew and kind of shifting. And notice when the pi is equal to 0.5, the distribution is in fact perfectly symmetrical. Now, as pi starts to grow and the probability of success increases, what we would see in the binomial distribution is that it would go from positive skew to negative skew. And if we had a probability of success of 0.95, we would have almost an exact mirror image of this component here, the pi of 0.05, except it would be on the other side of the distribution, or the other side of this page, but it would be the same type of skew except in the negative direction, with the highest bar being at 10 instead of at 0. What happens to the binomial shape as n changes? Now notice here that here if we start with a small number of trials, or n is 7, notice we have a fairly strong positive skewed distribution. But as the number of trials increase, what you will see here is that the distribution is starting to become more symmetrical and normalizing. So as n increases, the shape of the distribution begins to normalize. Let's try one more example. Suppose a die is tossed 5 times. What is the probability of getting exactly 2 4s? So this is a binomial experiment in which the number of trials is equal to 5, the number of successes is equal to 2, and the probability of success of a single trial is 1 over 6, or about 0.167. Therefore, the binomial probability equation is 5 combination 2 times 0.167 squared times 0.833 cubed. And that would mean the probability of tossing a dice 5 times and getting exactly 2 4s is about 16.1%. Shortcuts for the combination rule. So let's start with this one. Let's say we have a question that had something like this: 10 combination 0. Okay, so let's work this through. So we have 10 factorial over 10 minus 0 factorial times 0 factorial. So 10 minus 0 factorial is simply 10 factorial. So the numerator is 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. And our denominator is same, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. And what we know is 0 factorial here is also equal to 1. So what's going to happen here? Well, this whole numerator goes away, denominator goes away, and 10 combination 0 is equal to 1. So we can write this as a special rule to say n, any trial number, combination 0 will always be equal to 1. This helps reduce some of the steps of the calculations that we have to do. Next rule. Let's say we had something like this, 5 combination 5. So 5 combination 5, we have 5 factorial over 5 minus 5 factorial times 5 factorial. 5 minus 5 factorial just becomes 0 factorial, so we can just ignore that. So we have 5 factorial divided by 5 factorial, which of course if we write all this out, everything cancels out, and we end up with 1. So the rule we can state it as n combination n was number of trials, combination number of trials. So this is like the number of successes would be equal to the number of trials. That would be also equal to 1. Last shortcut rule, and that is trying this 5 combination 4. So 5 combination 4, we have 5 factorial, 5 minus 4 factorial times 4 factorial. Well, let's work this out. So we have 5, 4, 3, 2, 1 in the numerator. In the denominator, we have 1, 5 minus 4 factorial, so 1 factorial, times 4, 3, 2, 1, which is 4 factorial. So let's once again cancel all our like terms. And what do we end up with is just 5. So the rule this generates is the number of trials n, combination n minus 1 would be equal to n. So just a simple version of each of these, let's try something like this. For the first rule, 100 combination 0 is equal to 1. 100 combination 100 is equal to 1. Okay, and last one, 100 combination 99 would also be equal to 100. So these are your shortcut rules for combinations. This will help reduce the number of calculations that you'll have to work through. So shortcuts, once again, n combination 0 is equal to 1. N combination n is equal to 1. N combination 1 is equal to n. And n combination n minus 1 is equal to n. Cumulative binomial probability distribution. So the binomial refers to the probability that a binomial random variable falls within a specified range. For example, things like is greater than or equal to a stated lower limit and less than or equal to a stated upper limit. So for example, in the case of the airplanes we looked at earlier being late, we could look for something, instead of looking for a probability that none of the flights are late, we can say something like, what is the probability at least one flight is late? Or what is the probability that more than 3 flights are late? Or what is the probability that less than 4 flights are late, etc. So here we're looking at these inequalities in terms of looking at a range of possible outcomes, right? And the most simple way I can put this is it's all about calculating the separate probabilities of the specific discrete values and then summing across. At this point, I recommend you pause, read through the question before you proceed. The video will actually show you how to work through this full problem. Let's work through an example. According to petsite.com, 60% of all pet owners would get their next dog or cat from a shelter. Consider a random sample of 10 pet owners. We're going to define X, or our success in this case, as an owner who would acquire their next dog or cat from a shelter. So defining success would be someone that gets their next dog or cat from a shelter. What is N, our sample size? Well, we have 10 pet owners. Next, what is pi, the probability of success? The probability that a pet owner would get their next dog or cat from a shelter based on the poll is 0.6. Now, what are we going to find here? First, we're going to find the probability that more than 8 owners will adopt a pet from a shelter. So here we write out the probability statement as probability that X is strictly greater than 8. The second one we'll find is what is the probability at most 3 owners will adopt a pet from a shelter. At most 3 means that it's 3 or fewer. So basically we write that as the probability that X is less than or equal to 3. Then we'll find the mean and the variance and standard deviation of this distribution. But let's start off by finding the probability that X is greater than 8. So first, since we're looking for the probability X being greater than 8, we want to think what is greater than 8, right? We know that it could be probability that 9 people adopt a pet from a shelter and the probability that 10. Why don't we go anywhere past this? Well, because we're constrained by the number of trials or people here in this case, which is 10. Why aren't we including 8? Because this is strict inequality that excludes 8. We're interested in more than 8, not 8 or more. So let's find these probabilities. Let's start by finding the probability that X is equal to 9. So our equation is 10 combination 9, 0.6 to the 9th, and 1 minus 0.6 to the 10 minus 9. So first, using the rules we learned earlier, 10 combination 9 is basically n combination n minus 1. So we know in those cases that's always equal to n. And so 10 combination 9 is equal to 10. Now we need 0.6 to the 9th, which is 0.0100, we'll say 8. Finally, we need 1 minus 0.6 to the 10 minus 9, and that's just going to be to the 1, and 1 minus 0.6 is just 0.4, so we just have 0.4. So the probability that X is 9 is 10 times 0.01008 times 0.4, which equals 0.0403. So what does this say? It says that if we wanted to know the probability that exactly 9 people will adopt their next dog or cat from a shelter, it would be 4.03%. But this isn't the end of our task. The next thing we need to do is we need to find the probability that X equals 10. So the probability X equals 10, we have 10 combination 10, 0.6 to the 10th, 1 minus 0.6 to the 10 minus 10. Now in this case, we can easily see what's happening here. We recall that anything combination itself is going to be equal to 1, so that goes away. 1 minus 0.6 to the 0 in this case is just also going to be equal to 0.1. So we only need to find the basically what is 0.6 to the 10th, which is 0.00604. So of course the probability that X is 10 is 0.00604. So now we have enough information to be able to answer the question, what is the probability that X is greater than 8? Well, again, that includes probability X is 9 plus probability X is 10. So we have 0.0403 plus 0.00604, which equals 0.04634. Or we can write this as that the probability that more than 8 people will select to purchase their dog or cat from a shelter is going to be 4.634%. Now let's find the probability that at most 3 owners select their dog or cat from a shelter. So now we're looking for the probability that X is less than or equal to 3. So what does that mean? That means we need the probability that X is equal to 0, so no one adopts a pet from a shelter, plus probability X is 1, plus probability X is 2. And since this is inclusive with at most 3, then we also need to add probability that X is 3. So this is a little bit of a longer process. Okay, so let's get started. Let's start by finding probability that X is 0. So for X is 0, we're looking at 10 combination 0, 0.6 to the 0, 1 minus 0.6 to the 10 minus 0. So in this case, we only really need to find this probability here, which is basically 0.4 to the 10th, which equals 0.00010486. Next, we need probability that x is 1. So we have 10 combination 1, 0.6 to the 1, 1 minus 0.6 to the 10 minus 1 is equal to 0.001573. Probability that x is 2, we do 10 combination 2, 0.6 squared, 1 minus 0.6 to the 10 minus 2, and after some calculation we get 0.0106. And finally, probability that x is equal to 3 is 10 combination 3, 0.6 to the third, 1 minus 0.6 to the 10 minus 3. And once again, after some work, we get that total is 0.042467. So to find the probability that x is less than or equal to 3, we have to add up all of these probabilities that we calculated in the previous step, and we find that the total is equal to 0.05476. So we'd say the probability that 3 or fewer people would, or at most 3 people would adopt their next pet from a shelter is 5.476%. Now, just a little bit of a separate question here, just to kind of go along with this. What if we were interested in finding the probability that x would be greater than 3? So remember, there's 2 ways to go about this. Either we can calculate the probability that x is 4, 5, 6, 7, 8, 9, 10, or we can calculate it this way. We can think of calculating as 1 minus the probability that x is not greater than 3 or less than or equal to 3. Since we've already done most of the work here, all we have to do is take 1 minus the probability that x is less than or equal to 3, which is 1 minus 0.05476, which equals 0.9452. So what does this tell us? It tells us that the probability that more than 3, strictly more than 3 people choose to adopt a pet from the shelter is 0.9452, or 94.52%. Finally, the last part of the question is to find the mean of this distribution, and recall the mean is just n times pi. In this case, n is equal to 10, pi is 0.6, so we expect 6 people on average to adopt their next pet from a shelter. And finally, this variance is equal to 10 times 0.6 times 1 minus 0.6, which is basically 6 times 0.4, or 2.4. And the standard deviation is square root of 2.4, which equals 1.549, or approximately 1.55. Okay, so that's basically the process you'd go through to solve a question similar to this. This here is just a summary of our findings. Basically, the highlighted in green is the probability that x is at most 3. So we have probability x is 0, 1, 2, and 3, and we have each of these probabilities. And in yellow, you'll have the probability that x is greater than 8, which is 9 and 10, as well. This is just a diagram of all of those probabilities in a distribution. And notice that just like what we found the mean to be 6, we find that the most common number of people that would adopt a pet from a shelter is going to be 6 as well. So this illustrates the shape of that distribution and all of the details in that distribution. The last type of distribution we're going to be looking at is the Poisson probability distribution. The Poisson distribution describes the number of times some event occurs during a specified interval. The interval may be time, distance, area, or volume, and one key is that in a Poisson distribution, there is no upper limit. The upper limit could be anything, and that's why what we'll see is in Poisson distributions, they are effectively always positively skewed. So what are some of our assumptions? First, the probability is proportional to the length of the interval. So the longer the interval, the larger the probability. Second is that the intervals are independent. The number of occurrences in one interval does not affect the others. Some examples of Poisson probability distributions, or when we would use Poisson distributions, is to find things like this. The number of misspelled words per page in the newspaper, the number of calls per hour received by Apple customer care, the number of points scored in a college basketball game, etc. Let's meet the equation for the Poisson probability distribution. So the Poisson probability distribution is found simply as the probability of x is equal to the mean occurrence, mu, which will typically be given to you in this type of question, raised to the x, which is the success that we're looking to find the probability of. Then you multiply that by e to the negative mu, and e is basically 2.71828, which is the base of the logarithmic scale. And then you divide that by x factorial. The mean of the Poisson distribution is simply n times pi, which is exactly the same as all of the means calculations for discrete probability distributions. Let's look at an example. So this question says the average number of homes sold by Acme Realty Company is 2 homes per day. What is the probability that exactly 3 homes will be sold tomorrow? So first, key criteria. The mean number of homes is mu equals 2. We are interested to find out what is the probability that exactly 3 homes, so x is 3, and e, of course, is just the 2.71828. So what is the probability that 3 homes will sell? Let's plug in the values into our equation. So first we have 2.71828 to the negative 2 times 2 cubed divided by 3 factorial, which turns out to be 0.18. So the probability that exactly 3 homes will sell tomorrow is going to be 18%. So the Poisson distribution is always positively skewed. Here you'll see that as mu, the mean, becomes larger, the Poisson distribution becomes more symmetrical, but never becomes symmetrical. So in this case, you'll look to see the means. Here's 0.7. Here we have a mean of 2. Here we have a mean of 6. You'll notice the distribution is going from an extreme positive skew to a symmetrical skew, but the symmetrical never really becomes fully symmetrical. It will always retain a positive skew. Here's another example. If a bank receives on average 6 bad checks per day, what is the probability that the bank will receive at least 2 bad checks per day? What is the probability it will receive 9 bad checks per day? Here, the average, or the mu, is equal to 6. The next video will go into detail of how to solve these problems. So here we're given the information that a bank receives 6 bad checks per day. So the mean is equal to 6. So we're looking for the probability that bank will receive at least 2 bad checks in a given day. So that means probability that x is greater than or equal to 2. Now, in this case, you may think we need to do the probability x is 2, 3, 4, 5, 6, 7, etc. But remember that there's no upper limit in the case of the Poisson distribution. And therefore, what we need to do is we need to use the complement rule. So when we're looking for the probability of a value being greater than something or more than, we have to use the complement rule. So we'd have to do the probability that x is less than 2, because this is obviously the opposite of x being greater than or equal to 2. So we'd need 1 minus the probability that x is 0 plus probability that x is 1. And we don't have to include x is 2 because, of course, this is a strict inequality. And 2 is on the other side of that complement rule. So let's get started. So first we need the probability of x being equal to 0. So our equation says we have mu to the x, so mu to the 0, times e to the negative mu over 0 factorial. Well, we know 0 factorial is just 1. We know anything to the 0 is 1. So we just need e to the negative 6, which equals 0.0025. So the probability that x is equal to 0 is 0.0025. Now we need the probability that x equals 1 before we can find the question, or answer the question that we are in fact trying to answer. So x is 1, we would do 6 to the 1, e to the negative 6 over 1 factorial. So we basically have 6 to the 1, which is 6, e to the negative 6, which is 0.0025 over 1. So the probability that x is equal to 1 is 0.01487. So to find the probability that x is greater than or equal to 2, we do 1 minus 0.01487, which is equal to 0.98513. So the probability that they receive at least 2 bad checks a day is about 98.51%. Okay, let's go to part B. Part B says, what is the probability that it will receive 9 bad checks on a given day? So this is simple. We just do probability that x is 9, and we do 6 to the 9th, e to the negative 6 over 9 factorial. So 6 to the 9th is equal to 100,776. E to the negative 6, as we found before, was 0.0025. 9 factorial is 362,880. So the probability that x is 9 is equal to 0.0688, or we could say 6.88%. So that's simply how we work through these Poisson distributions. Again, you can use the cumulative rule to calculate these, and of course the complement rule is very important because remember there's no upper limit. So whenever you're looking for a cumulative value, you must use the complement rule. When to use binomial versus Poisson. So Poisson. If a mean or average probability of an event occurring per unit time, per page, per mile is given, and you are asked to calculate the probability of n events happening in a given time, number of pages, number of miles, etc., that's your Poisson. And fact is, there's no clear upper limit with the Poisson distribution. Binomial. If an exact probability of an event happening is given or implied in the question, and you are asked to calculate the probability of this event happening k times out of n, we use our binomial. Binomial versus Poisson. A typist makes on average 2 mistakes per page. Let's think about, is this a Poisson distribution or would we use a binomial? So in this case, since there's no upper limit of the number of mistakes on a given page, it will be a Poisson. A computer crashes once every 2 days. What is the probability of there being 2 crashes in 1 week? Once again, no clear upper limit, therefore Poisson. Components are packed in boxes of 10. The probability of component being defective is 0.1. What is the probability of a box containing 2 defective components? That will be a binomial as we have an upper limit. ICs are packed in boxes of 10. The probability of an IC being faulty is 2%. What is the probability of a box containing 2 faulty ICs? That would again be binomial since we have an upper limit. Finally, the mean number of faults in a house is 8. What is the probability of buying a new house with exactly 1 fault? And once again, this will be a Poisson since we don't have a specific upper limit or a clear number of trials in this case. Now, For practice, I'd recommend trying to solve each one of these with the correct tool, and we will discuss them in our class next on Wednesday. That's the end of Lecture 6, Part 2.